did not discuss regarding alkyl fluorides. That is the fluoride group. I told you that there is one specific exception for that. So we will try to see that in today's class. And after that, whether E2 is stereospecific or regiospecific or not, we will see. And then we will be starting E1 CB. So I hope you have gone through the syllabus for this Saturday's test. So a lot of things have been included. We have alkanes, what you did in the last week. Added to that, you have keto-enol tautomerism along with GOC. I think only less percentage of questions will be asked from those two, GOC and keto-enol tautomerism. And you have alkenes, only two preparation methods, dehydrohallucination and dehydration. Actually, we are discussing all these mechanisms. If you see carefully, all of them are regarding dehydrohallucination, one of the methods. So once this dehydrohallucination is done, mostly we'll finish it by today's class. Tomorrow we can start dehydration. Same type of reactions only, but rearrangements will come when the rearrangement reactions we will see for alcohols, because yeah, we will see that will take hardly around 1 or 2 hours, nothing more than that. And then we can have time for revision. I'll revise and it will be easy for your exam and all. Okay, so let's start today's class. So in yesterday we have seen what are the alkyl halides between primary, secondary and tertiary, which are going to favor what type of reaction. And the other E1, E2 mechanisms we have seen. Added to that, the factors affecting both E1, E2 mechanisms also we have seen. So you have to be careful while you are writing the intermediate steps, because E1 mechanism rate determining step is different, E2 mechanisms rate determining step is different. Carbocation formation, a cation will form in E1, a neutral species will be there as intermediate in E2. So the corresponding stabilities of the intermediate will determine the course of mechanism. That's the reason why primary alkyl halide, it will not follow E1 because it will form a primary carbocation. So when it comes to carbocation, tertiary is more stable than secondary, more stable than primary. So the least stable carbocation cannot be formed as an intermediate. That's the reason why primary alkyl halide will follow E2 mechanism, where there is no carbocation formation, just a neutral species, the interaction of the base with the beta hydrogen and the leaving tendency of the halogen part. And coming to secondary and tertiary, they are relatively more stable than primary carbocation, like the intermediate secondary carbocation and tertiary carbocation are more stable than primary carbocation. And that's the reason why they can perform or they can undergo dehydrohallucination both by E1 and E2 mechanism. So what is the deciding factor? The type of base we are taking and the concentration of it. These two are the deciding factor. For E2, we require a proper interaction with the base during reaction intermediate formation, right? The transition state and all. So high concentration of a strong base will lead to E2 mechanism. And since E1 has nothing to do with the base, just its sole purpose is to remove the H plus, and that can be done by weak base also. So the lowest concentration of a weak base, any weak base, can proceed the reaction towards E1 mechanism. So I told you that while writing the nature of substrates and the leaving groups tendency, we haven't included fluoride. So we will try to cover dehydrohalogenation of fluoride in today's class, and after that we will start this one. Mm, E1CB mechanism. E1CB is specific. Most commonly encountered mechanisms are E1 and E2 only. E1CB is specific. So those specifics also I will give you a list, and that will be sufficient. Okay. So keep the side heading as dehydrohallucination, E2 mechanism, or E2 dehydrohallucination of, one second. Okay. So what's the date? 17th Feb. Okay. So keep the heading as E2 dehydrohallucination halogenation of alkyl fluoride. Specifically, we are seeing an exception for alkyl fluoride. So, if you remember, both in E1, E2, when we were writing the leaving group's capacity, iodide were easily removed than bromides, than chlorides, than iodides. And most of once all these leaving groups are being eliminated from our substrate, mostly we will use to get SAIDZEF product. Okay, SAIDZEF product is nothing but most stable alkene or most substituted alkene will be the major product. If it is a Halfman product, we used to get a least substituted alkene as our major product. Okay, so these two are the common things between E1 and E2. Now coming to E2 mechanism, especially for alkyl fluoride, we won't be getting the major product as SAIDZEF. Most of the cases, SAIDZEF product was the major product, right? If you remember, this was the major product, and this Hoffman product is only formed when there is steric hindrance. Steric hindrance due to bulky base or something like that, due to bulky base, or even it comes to even mechanism, the steric hindrance is offered by the substrate itself. So whenever we have steric hindrance, then only Hoffman product, that is the least substituted alkene, will be the major product. In all other cases, SAIDZEF product or the most substituted alkene should be our major product. So if you take any alkyl fluoride, the opposite will be the major product. For example, you can just make a note of it. So when it comes to E2 dehydrohalogenation, least substituted alkene after the removal of fluoride, the least substituted alkene will be the major product. Even if you don't have any steric hindrance both in substrate or in a base, the major product will still be the least substituted alkene. That is, the will be Hoffman product will be the major product in any alkyl fluoride. So what's the reason for this? What is the underlying mechanism, or what are the factors responsible for this least substituted alkene to be formed as major product? That we will try to see. So before we do that, let's take a small example. So we have CH3, CHF, CH2, CH2, CH3. So in presence of methoxide, this will be R base. So base is not bulkier, it is simple base only. Even there is no steric hindrance in the substrate, it is not branched at all. So even this is the case, the type of product formed, the major product will always be least substituted one only. CH, CH2, CH3, this is one possibility, and the other possibility is CH2 double bond CH, CH2, CH2, CH3. So this pent 2-ene, this is what we expect to be the major product, but this is formed in 30% only, making it a minor product. Whereas the other one, pent 1-ene, this is formed 70%, making it as major product. So this is opposite to the concept that we have learned till now. If we don't have any steric hindrance or any other things stopping the base to remove the beta hydrogen, we are supposed to get the most substituted, that is pen-2-ene as our major product. But in these alkyl fluorides, E2 mechanism, E2 reaction, we are getting the expected product to be minor, and the other one, the which we don't involve or which we attribute less stability, as the major product. So what's the reason for this? So there are more than one dynamics involved in this sort of E2 reaction for alkyl fluoride. So let's see the reason for the change in the major product for alkyl fluoride. So as you can see, in the leaving group tendency, if you see the above order over here, if you see the leaving group tendency, F minus is the least preferred or least leaving group. So when it comes to F minus group, it is the least or poor leaving group, which means it cannot be easily removed. And as long as we remember dehydrohalogenation, the hydrogen part at the beta position and the halogen at the alpha position should be removed so that a new pi bond will form and alkene will be our product. Now, when it comes to fluoride, because of its smaller size and greater electronegativity, all these things concerned, the bond is very strong between carbon and fluorine, making it a poor leaving group. And because of that reason, if we try to see the transition state, so this is our example, right? So let us try to write the transition state for the above example. So what do we have? There are two possibilities. So this is our CH3, CHF, CHF. If we take this beta hydrogen, so H, CH2, CH3. So this is alpha hydrogen, beta hydrogen. Now in the another case, what do we have? CH2, H, CHF, CH2, CH2, CH3, and the base will be interacting here. CH3, O minus, and here also O minus, CH3, right? So this will be our possible transition state 1 and possible transition state 2. Transition state 1 and transition state 2. Here I did nothing. Whatever the two possible beta hydrogens we have, this is one beta carbon, this is the other beta carbon. I wrote the possible transition state. So we will try to analyze what are the dynamics involved or other underlying factors. So one thing, it is pretty clear that F minus is a poor leaving group. It cannot be easily removed. And during E2 mechanism, the first and foremost thing that will happen once the transition state is formed is the removal of halogen part as F minus, and the base will be regenerated. Alcohol CH3OH will be formed, right? But this F minus cannot be easily removed. This cannot be easily removed, but the base will be strong, it will be efficient, and it will be removing the H plus. Because of that, a negative charge will start appearing on the carbon. So I'll repeat again. When it comes to E2 mechanism, F minus should be removed, H plus should be removed. H plus removal can be easily done by the base because obviously we are using a strong base. Now, coming to the removal of F minus, because F minus is a poor leaving group, it won't leave the molecule, it just stays in its position only. But the removal of hydrogen will be done, right? It will be removed as H plus. If this is removed as H plus, a negative charge will appear on this particular beta carbon. So beta carbon, when base abstracts beta hydrogen, F minus has less tendency to leave than other halides. So a negative charge will appear on beta carbon. A negative charge will appear on beta carbon, and the transition state gets carbanion character, and the transition state gets carbanion character. So even in the second possible transition state also same thing happens. H plus will be effectively removed, F stays in the substrate itself. Because of this H plus gone, this carbon, the beta carbon, will get a negative charge in the next step. So let me write that step also. Then we will try to understand the type of groups attached to the carbo carbanion. So after the loss of H plus, the molecule, the carbanion will look something like this. So we have FCH minus CH2 CH3. So this is 1, and we have CH2 negative charge, CHF, CH2, CH2, CH3. So this is our second one. As you can see, there is a negative charge developed on the beta carbon. This is alpha, this is beta, this is alpha, and this is beta. This negative charge gives the reaction intermediate a carbanion character. Here, this definite carbanion will not be formed, but there will be a shifting of charge, that is a negative charge will appear on the beta carbon. Now in the previous mechanisms and all, we used to remove this F minus, this positive charge on this carbon used to help in the new pi bond formation. This lone pair will be donated over here and a new pi bond used to form. But now, since F minus cannot be easily removed, it gives carbanion character. Now we have to discuss the stabilities of these two carbanion, so that the most stable carbanion, that will give us the most or the major product. Now let's see how can we determine the stabilities of these two carbanions. So if you see, this is plus I group, this is minus I group, right, to the carbanion. Now this part is plus I group, right, plus I effect. Okay, product 1, transition state 2. Now here also this is minus I group and this is plus I group. So if you remember in the electronic effects, what are the groups that will increase the stability of carbanion? So carbanion stability. So what are the groups? The stability is directly proportional to what? Plus I group or minus I group? The negative charge should be easily evenly distributed, or it should be increased? Minus I group, very good. So the stability of carbanion is directly proportional to minus I group and inversely proportional to the plus I group. So in the first compound, as you can see, there are two plus I groups, methyl groups and ethyl groups. In the second one, there is only one plus I group, that is propyl group. Negative I effect is there definitely, and it is common in both of them. The magnitude of plus I effect is more in a first transition state than in second transition state. So this will be, so wait a second, yeah, it will be more, and minus plus I group and plus I group, pent 1 in is more stable. Yes, so there are two plus I groups which are okay, magnitude of plus I for propyl group will be greater, and it is acting in the same direction. So electron will shift over here towards Fi, and here the electron donation will happen in this direction. So overall this will get cancelled, whereas over here the electron cloud will shift towards in this direction, and over here in this direction, and over here in this direction. So when it comes to the first, what is the possible product for the first transition state? CH3 CH double bond CH CH2 CH3. So this is pent 2 in. Now when it comes to the other transition state here, what will happen? The possible product for the two, you have CH2 double bond CH, CH2, CH2 and CH3. So the groups which will increase the stability, the plus I groups and minus I groups, whatever we have, the number of plus I groups are more over here, first thing. And second thing, what is the type of carbanion over here? Let me change the color. It is a secondary carbanion. Over here, this is a primary carbanion. And what do we have? Carbanions order. Tertiary is less stable than when you have plus I groups. Tertiary will be a reverse of carbocation stability. Primary will be more stable than secondary. Secondary will be more stable than tertiary carbanion when you have the opposite of the carbocation stability. So first thing, more number of plus I groups are there in the first compound. Added to that, this is a secondary carbanion. In the second one plus I group is there. Added to that, whatever the carbanion that we have here, it is a primary carbanion. So this will be more stable. So this will be more stable carbanion than the first one. That's the reason why pent-1-ene will be our major product and pent-2-ene will be our minor product. So just because fluorine is poor leaving group and due to that the intermediate is getting a, a, a carbanion character, and this carbanion stability is dependent on the number of plus I groups, number of minus I group, all these things considered, the least substituted alkene, which will be due to primary carbanion, which will be formed due to primary carbanion, will be a stable intermediate comparatively. Because of that reason, when it comes to alkyl fluorides, the major product will be the least substituted alkene, the least substituted alkene. Major product will be the least substituted alkene. So this is one thing. So did you understand? So what's the reason behind all this means? First thing is F minus being a poor leaving group. Because of that, we are getting a carbanion character, a negative character. Okay. And second thing is the stability of the so formed carbanion. Stability of carbanion, which will be primary greater than, secondary greater than tertiary. And using these two logics, we have given a justification why Hoffman product is the major product during uh, dehydrohallucination of alkyl fluorides. Is it clear, or do you need me to explain again? I'll do it one more. Okay, I'll go to the starting. I'll do it one more and then we can move forward. So when it comes to alkyl fluoride, fluoride being more electronegative on the smallest atom, it cannot be easily removed as F minus. So if F minus is not removed during the transition state and H plus is removed, the beta carbon will end up having a negative charge. Now the number of groups attached to this carbon with the negative charge will determine the stable carbanion, and the stable carbanion will give the corresponding major product. Now between 1 and 2, for this beta carbon, first thing is it is secondary carbanion. Added to that, there are more plus I groups which will further increase the electron density, which will further increase the negative charge on this. Because of that, it will be less stable carbanion. And coming to the second transition state, first thing, whatever the carbanion it is formed, it is primary carbanion. Added to that, the plus I effect, only one group is there. So more stable primary carbanion along with that less number of plus I groups. Combining these two factors, this primary carbanion will be the more stable carbanion. Now, this more stable carbanion will be giving us the major product, which is the least substituted alkene, or we will be calling it as Hoffman product. Simply we call it as Hoffman product. So this is about dehydrohallucination of alkyl fluorides. Clear, right? Okay. Now, yes, please.
Can you explain fluoride and why it is a poor living group?
Why it is a poor leaving group? Because F minus is a strong base. Yeah, okay, let's not go there. F minus, see, carbon fluoride bond you compare, carbon iodide bond we will try to compare. 1 second. So when it comes to carbon fluoride, carbon chloride, carbon bromide, and carbon iodide, this is more electronegative, right? Even if there is proper shifting of electron cloud, the bond dissociation enthalpy will be less for carbon iodide than it is for carbon fluoride. First thing. So because of that reason, I minus can be easily lost, easily removed. So I minus will be easily removed than bromide, than chloride, than fluoride. F minus is the poor leaving group. Because of its small size, it will be properly bonded and the bond dissociation energy will be more. That's why it cannot be easily removed. More amount of heating or some much stronger base when compared to the other halides will be required. So of all the halides, fluorides will be the poor leaving group because of the greater bond dissociation enthalpy or higher electronegativity. Also we can attribute to fluoride while removing the fluoride. Okay, because it cannot be easily removed. The actual dynamics, if you remember, if this is fluorine and if it is hydrogen, this alpha and beta, this will be removed as H plus, so you will have a negative charge. This will be removed as F minus, so it will have a positive charge. These electrons will be donated over here, and in the next step, you will have carbon-carbon double bond. If fluorine itself is not leaving and there is only negative charge, then it will lead to the carbanion formation, which is exactly happening here. Okay. Right.
Yes.
Right.
Mom, and
All right.
this one is the rate determining step.
Same. Only one step, single step only. Here for explanation part, I have written more than one step. Just like E2, here also only single step. Rate determining step will only be one. So let me write that also. Rate determining step. So we have CH3, CHF, CH2, CH2, CH3. In presence of CH3O minus, you will have a transition state something like this. CH2, H, C, F, H, CH2, CH2, CH3. This will be bonded to CH3O minus. So this will be a transition state. And the next step we have CH2 double bond CH, CH2, CH2, CH3. Only single step. This is the slow step and the rate determining step, the formation of the transition state. Just like normal only. Only thing is the major product will be different from the usual E2 products. In this case, as an intermediate is formed, will rate depend on base concentration? Definitely, it is still E2 reaction only, right? It is, even if there is carbanion or single one in the intermediate, both the base and the substrate are present. It is still E2 reaction only, no doubt in that. The rate is still proportional to the substrate, concentration of substrate and the concentration of base, no doubt in that. But the major product formation will only be different when it comes to alkyl fluoride. It is still E2 only, both concentration of base and this thing, uh, concentration of base and the concentration of substrate are directly affecting the rate of reaction. Anywhere it is least substituted, can it call it Hoffman product even if there is no hindrance and all? Yes, that's what. Even if there is no hindrances, Hoffman product is nothing but least substituted alkene only. The the factors leading to the Hoffman product were steric hindrance in some scenarios. As long as the final product is least substituted alkene, we can call it as Hoffman product. Yes, we can call it actually. So that is one thing. Yeah, don't forget, it is still E2 only. The concentration of base, the strength of the base, and the concentration of the reactant will definitely affect the rate of the reaction. Only thing is the major product will be different from the rest other products. That's it. CH double bond CH, CH2, CH3. This is what we expect, but this is going to be our minor product. Okay. All right. So this is about dehydrohallucination of alkenes. Dehydrohallucination of alkyl fluorides. Main reason is F minus being poor leaving group results in carbanion character, and the usual stabilities of carbanion character are decided by whether it is a primary carbanion, secondary or tertiary, and the type of groups attached to this carbon with a negative charge. So by keeping these two factors, we can determine the major product. Okay, so that is one thing. Now, if you remember, whether stereo or regio selective, we have discussed, right? So when it comes to stereo selective or regio selective, the major product will be specific isomer, or a specific product will be the major product. That's what we compare when we are trying to determine whether it is stereo selective or not. I told you there is one more term called as stereo specific. So this stereo specific, we will try to see whether E1, E2 below or stereo specific or not. So when it comes to stereo specific, the keyword will be elimination of specific beta hydrogen atom. So when it comes to stereo selective, selectively a particular isomer, a particular product will be formed. So when we are trying to say whether a given compound is stereo specific or not, we will be looking at what type of elimination or what is the atom that has been eliminated during the reaction. Uh, can we say that in case of alkyl halides, elimination through E2, the major product is always the Hofmann product? No, 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 no. Most of the cases, elimination reaction will give Saytzeff product only. That is more substituted alkene. If you have alkyl fluorides or steric hindrance is present in the base or in the molecule, then only Hofmann product will be formed. Always major product during dehydrohallucination will be Saytzeff only, ma. Don't get confused. That is more substituted alkene. Please don't get confused. Major product will always be Saytzeff only. Only in case of exceptions. Exceptions include alkyl fluorides or bulky substrate or bulky base. During these things only you have major product as a Hofmann. Okay. All right. Chalo. Coming back, stereo specific. So the keyword they give a lot of explanation for this in all, like whatever the books I have gone through. There were a lot of explanation, but I will give you simple logic to understand. Elimination, what exact beta hydrogen is eliminated, whether the reaction is specific towards the hydrogen elimination, that will help us determine whether it is stereo specific or not. So what happened? Does the least substituted alkene have to be a major product to be called as Hofmann product, or it can be Hofmann product even it is not a major product? Yes, it need not to be a major one. As long as it is least substituted alkene, we call it as Hofmann product. No need to be major percentages for it to be called as Hofmann. As long as it is least substituted, we call it as Hofmann. So that is first doubt. Second doubt, major product is Hofmann, even the substrate is having steric hindrance. Definitely, if there is steric hindrance to beta hydrogen, so let's say you are having substrate, and in that substrate, the steric hindrance should be towards beta carbon. So let's say if this is alpha beta, this should be bulkier. This is beta carbon, right? So this should be bulkier group. There should be steric hindrance for the base to attack the beta hydrogen. So yeah, for the substrate, there should be steric hindrance towards the beta hydrogen attacking, or else even bulkier base by default, the major product will be the Hoffman product. Okay, clear, right? Still any more doubts on major minor product regarding Hoffman and Saytzeff elimination? All right. Okay, coming back to the stereospecific reaction or not. We will be specific. Specific means towards the elimination of a certain beta hydrogen atom only. Now, if you go through the examples that we have discussed in all sorts of E2 mechanism, every time we used to write the halide part and the beta hydrogen part, something like this. So if this is our halide and CH3. Always we used to write the fluorine and hydrogen in the transposition or in the antiposition. So this is trans, right? This is E2, CH3O minus. Okay. So this is our E2 transition state. When it comes to E1, it was just a carbocation. So when it comes to E2 mechanism, E2 reaction, the leaving groups, what are the leaving groups here? Halogen and the hydrogen, both. So the leaving groups at alpha carbon and beta carbon and base should be in antiposition, should be in trans or antiposition. Antiposition, that is, they should be coplanar. All of them should be in the same plane. They should be coplanar. Then only the elimination will happen smoothly. So this kind of specific orientation of beta hydrogen on the beta carbon is called as trans elimination. Trans elimination, and this is only seen in E2. Only E2 has this specific rule where the leaving group, the F minus, the hydrogen part at the beta carbon and the base part, all of them should be at right angles. Right angles in the sense they should be in the opposite sides. They should be in the transposition. Only then they can be easily removed. This is called as trans elimination. So you might be having a doubt. Generally, we call cis and trans for alkenes on red. So for alkanes, why are we giving that specific orientation? Okay. So when it comes to alkanes, there will be free carbon-carbon or free sigma bond rotation. Free sigma bond rotation. So the leaving groups, will arrange themselves, in transposition during E2 reaction. So this is there. But when it comes to alkenes, even alkenes can undergo this E2 mechanism, right? So for example, if you have C double bond C, some Cl, H, or let me show you one more. Yes, Cl. So in presence of a base, even this can undergo, and C triple bond C, H and H. So this is opposite, and to this hydrogen you have OH minus. This is gonna interact. So this will be removed, this will be removed, and a new pi bond will be formed. As far as alkanes is concerned, just because sigma bond rotation is there, it can orient itself and undergo E2 reaction. But as you go for alkenes, dehydrohallucination of alkenes, then it should always be a trans isomer, always be a trans isomer. So here during the elimination reaction, the beta hydrogen or the base trans elimination is specifically removing a particular type of hydrogen which is in transposition. So here a specific hydrogen is removed. That's why E2 is a E2 is a stereo specific reaction. If the hydrogen is present in the transposition with the halogen part, then only E2 elimination will happen. Otherwise, it won't be E2 elimination. So E2 is stereospecific. The base will be specific towards the hydrogen. It is going to remove. So this is stereospecific. So on this basis, are there any specific during even reaction? Are there any specific for the removal of beta hydrogen? No, right? As long as beta hydrogen is available, the reaction can undergo E1 mechanism. So E1 is not stereospecific. E1 is not stereospecific reaction. So when it comes to E2, the orientation of hydrogen is important for it to be eliminated by the base. That's why it is stereospecific. Whereas E1, as long as it is beta hydrogen, then it will be even elimination only from the in carbocation. As long as there is beta hydrogen available, the base just simply removes it and forms the alkene. So there is no specificity towards beta hydrogen removal in E1, whereas in E2, the one which is present in transposition, only that will be removed in E2 mechanism or in E2 reaction. So what are the two terms that we have seen? That is stereospecific and stereoselective. So when it comes to E1, this is not stereospecific, but it will be stereoselective. Why? Because SADZF product will be our major product. The most substituted alkene, the major product will be SADZF product. Whereas when it comes to E2, a particular beta hydrogen will be removed. So it is stereospecific. It is also stereoselective. Why? Because most of the cases, the major product will be SADZF only. Only you have, again, only in exceptional cases like alkyl fluorides or due to steric hindrances, then you'll have Hofmann product. Other than that, the reaction will always be ending with the major product as the most substituted alkene or the SADZF product. So this part, this table is important. So they will give you a substrate, any alkyl halide, very important. So they will give an alkyl halide, they will give you a base, and you have to estimate what is the type of reaction it can undergo. If so, is it stereospecific or not? Is it stereoselective or not? So the questions can be asked in that approach. So understand the difference. Specificity is towards the elimination of the beta hydrogen. Selectivity is towards the product formed at the end of the reaction. Both E1 and E2 are stereoselective. Only E2 is stereospecific because trans beta hydrogen will only be involved in the elimination during E2 reaction. Clear, right? Actually there are a lot of dynamics involved here, but I try to give in simple words because all those stuff anyway is in advanced level only. We need to understand the logic behind it. Okay, so that's why stereospecific and stereoselective. Simple word. Specificity is towards the elimination of beta hydrogen. Selectivity is towards the product formed at the end of the reaction. All right. So this is about E2 reaction or E2 mechanism. Now we will go for E1CB. E1CB is going to be a little bit different, and you can treat it as an exceptional case because not all alkyl halides will show E1CB mechanism. Okay, so before I start E1CB, is this part clear for everyone? Do you need some more clarification? Let me know. All right, so I'll take this as what happened. Mm, uh, till once again, yes, I'll explain once again in brief. So till where is the portion? Whatever we are going to finish this week, everything like till Friday, it will be the portion actually. E1, E2, E1CB mechanisms are there. They are specifically for alkyl halides, and rearrangement reaction will come in alcohols. Whatever we are going to discuss till Friday will be the portion for Saturday. Okay, once again, a brief recap for this stereospecificity. Stereoselective or regioselective, if you remember, we defined it as the reaction, the course of the reaction will always be to form a more stable product, which means the products formed are selectively formed in such a way that we end up having a more substituted alkene as our major product. So the course of the reaction is done in such a way that ZF product will be our major product. That is called as stereoselective. If specific type of isomer is the major product, then it is stereoselective. Now, coming to the stereospecific. Specificity is towards the elimination part. During the intermediate formation, the base will be extracting H plus, right? During that step, if base has any criteria, no, I am going to remove only beta minus, beta hydrogen only, that too in particular transposition. Then it is called as specific, stereospecific reaction. When it comes to E2, the hydrogen should be in trans. That's why it is stereospecific. Whereas it comes for E1, as long as you have beta hydrogen, then it will be fine. We will get as an alkene as our product. So E1 is not stereospecific, but it is stereoselective. E2 is stereospecific, also stereoselective. Okay, I will send a chart. Actually, there is a good chart in Cengage combining E1, E2, and E1CB mechanisms. So once we do E1CB today, I will share that part so that all like it will be a comparison, point to point comparison will be there. All right. Now please take down the next heading as E1CB, E1CB mechanism or E1CB reaction. So E1CB. So E1 stands for elimination unimolecular only. This is also elimination reaction. Elimination reaction. This suffix 1 indicates unimolecular. Unimolecular in the sense in rate determining step only one substrate or only one component will be there. Unimolecular. 1 stands for unimolecular and CB stands for conjugate base. CB stands for conjugate base. So what do we mean by conjugate base? So if you take a simple example, if you have HCl, so it is an acid, right? After H plus is lost, the acid turns out to be Cl minus. So this is for an acid, you have conjugate base due to loss of H plus. So if you take H2SO4, so after one H plus is lost, you have HSO4 minus. So this will be the conjugate base. If you take HNO3, same. After H plus is lost, you will have nitrate, NO3 minus ion. So this will be the conjugate base. Conjugate base is nothing but the anionic part resulted due to loss of H plus. So in this E1CB mechanism also, we will be writing all the reaction step by using the conjugate base of our substrate. So let's see how this reaction mechanism will goes on. Are there any specification? All those sorts we will try to write. So E1CB mechanism. So in E1CB mechanism, there are two steps. It is a two-step mechanism. So step one. So whatever the substrate you take, that substrate will be a conjugate base, which is carbanion, which is a carbanion, which is a carbanion will be formed. Hmm. Hello. Am I audible now, guys? Am I audible now? Hello. Am I audible now? Is it fine? Is it fine? Okay, sorry. Yeah, like the thing is, I'm in PG, right? Sometimes the network will fluctuate, the bandwidth will fluctuate, and that's the problem. So yeah, this will be for few days only, ma. I'll try to arrange for something alternate. Okay, so coming to the step one, when it comes to E1CB mechanism, whatever the substrate you have, from substrate or the reactant, first step H plus will be lost and you will end up having a conjugate base. This conjugate base it will be an anion, specifically carbanion, carbon with the negative charge. So from the start of E1CB, okay, sorry. Okay, so when it comes to E1CB mechanism, it is also an elimination reaction. That's why the letter E. And the suffix 1 it will indicate unimolecular, just like it did in E1 reaction. Now, what does the small letter CB will indicate? The small letter CB will indicate conjugate base. Conjugate base is nothing but after the loss of H plus, whatever the anionic part you have, that part is called as conjugate base, and it will be always due to the loss of acidic proton, that is H plus. Even H2SO4 is an acid, right? After it has lost its H plus, we will be getting HSO4 minus ion. So this will be the conjugate base. Even for nitric acid, after the loss of H plus, we will be getting nitrate ion, NO3 minus. This will be conjugate base. So I hope you got the idea of conjugate base. Any molecule, after losing its H plus, it will form an anion. That anionic part is called as conjugate base. So when it comes to this particular elimination reaction, it will be due to this conjugate base formation. That's why the specific name. That's why the specific name, conjugate base, elimination unimolecular conjugate base. These are the three keywords in E1CB. Okay, and what is the mechanism? Before I give before we see the proper mechanism and all, just write what exactly happens in E1CB. This is a two-step reaction. In the first step, conjugate base formation will be there. And how is that conjugate base formed? By losing H plus. After losing H plus, obviously a negatively charged conjugate base will be formed. And since we are in organic part, converted to alkene in the step number 2. But even it seems to be simple, when we go into proper mechanism, lot of things have to be taken care of. So let's see what exactly it will be. So let's take a simple example. CF3 CHCl2 in presence of a base, ethoxide C2H5O minus. Mm, voice broke. Acha, I'll repeat again. Okay, I'll repeat again, ma. Since from starting, I'll repeat again. So when it comes to E1CB mechanism, So when it comes to E1CB mechanism, it is also a type of elimination reaction only. But the thing is, the reaction rate determining step is the one we consider while stating whether it is a unimolecular, bimolecular, something like that, right? So that rate determining step contains only one substrate, so that's why it is unimolecular. Added to that, it is a conjugate base. A conjugate base in the sense the anion formed by the loss of H plus. So if you take any normal acid as an example, after losing H plus, you'll get an anion, right? That anionic part is called as conjugate base. If you take H2SO4, this is acid. After losing H plus, we will end up having HSO4 minus. So this is the conjugate base. Conjugate base is nothing but the anion formed by the loss of acidic proton, that is H plus. Now, in this E1CB mechanism, we do have a substrate, a reactant, where in the first step, a conjugate base formation will be there. And how exactly this conjugate base is formed? Same like any other acid, H plus will be lost. By the loss of H plus, a carbanion, which is our conjugate base, will be formed. Now, in the second step, this carbanion will be converted into alkene. So this conversion of alkene is our rate determining step, RDS. This will be our rate determining step. Carbanion, carbon with a negative charge, will be formed by the loss of H plus, or in the second step, this carbanion will be converted into alkene. And not all alkyl halides will show this particular E1CB mechanism. There are specifications. Specifications I will give, but first we will see how exactly this will work out, and then I will give the conditions to show this particular E1CB mechanism. So let's take this example, CF3CHCl2. All right. Now, this is our beta hydrogen. This is our alpha, F is our leaving group, and this is our beta. So why I'm taking like this also, once I give the condition, you will understand. You might be having a doubt, why can't carbon with the chlorine can be taken as alpha hydrogen, alpha carbon? That part also I will give you explanation. But first let us write the basic example. So you will be having CF2 double bond CCl2 by the loss of F minus, and H plus will be lost along with the base. So just simply write the alkene part. Okay, now let's see step by step what exactly happens. Step 1. So mechanism I am writing. Mechanism. Step 1. So what is our step 1? Conjugate base formation, that is removal of H plus. Why is F being lost? Yes, I will tell you why FB is being lost. So the main condition, okay. Is it tendency? Yes, it has least tendency to leave. But okay, the criteria is we need to have at least one beta hydrogen for it to have an elimination reaction, right? So the only hydrogen available is on this carbon. So if this hydrogen should be removed, then the only possible halide part that we can remove is fluorine only. We cannot remove chlorine. It is possible, but it does not give us alkene as the product. That's why for hydrogen to be in beta position, the carbon with the fluorine substituent should be the alpha carbon. That's the reason why fluorine is eliminated in this reaction. Okay, you got my point. That's the criteria for elimination to happen. Beta hydrogen should be removed, right? Dehydrohalogenation. Dehydrohalogenation. Halogenation will be, halogen group will be from alpha carbon, hydrogen will be from beta carbon. That's why. Okay, right. All right. Now, coming to the mechanism part, first step will be the loss of H plus and conjugate base or carbanion formation. Carbanion formation. So what is our initial reactant? So carbon, carbon, fluorine, fluorine, fluorine we have, hydrogen we have, chlorine and chlorine. So in the first step, because of the base C2H5O minus, this H plus will be removed and it will give us a carbanion F, F and F, Cl, Cl. You have a lone pair with a carbon with a negative charge. So this is first step only. So this is first step. So it is not the rate determining step. So the first step will be the formation of carbanion or conjugate base formation. Why we are calling it a base? H after H plus is lost, whatever might be the compound, it will be like obviously it will be anionic part. It will be treated as conjugate base. Now let's talk about step 2. What is the step 2? Carbanion to alkene formation. Carbanion to alkene. So what is the carbanion here? F, F, F and carbon with a lone pair negative charge, chlorine and chlorine. So whatever might be the position, as long as hydrogen is removed, it will be beta. So this will be our alpha. So this will be our alpha and here also this will be our beta. So the lone pair, whatever the carbanion is having, they will form a new pi bond over here. And this carbon fluorine bond will be withdrawn by the fluorine. So in this direction, the electron shift will happen. So fluorine will be lost as F minus and you have fluorine, fluorine, double bond C, Cl and Cl. So I just wrote you to show what fluorine is lost, but you can write CF2 double bond CCl2. So 1 comma 1 dichloro 2 comma 2 difluoroethane. So this is our alkane. This will be our product. This will be our product. Okay. So what is the, how come the alkene is formed? From anion, the lone pair on the carbon is forming a new pi bond between alpha carbon and beta carbon, and this fluorine will be undergoing heterolytic cleavage. F minus will be lost and you will have 1 comma 1 dichloro, 2 comma 2 difluoroethane. Substituted alkene we will get, halogenated substituted. So what is the step here? And this is the rate determining step. This step 2 is the rate determining step and this is the slow step. So how many substrate or how many reagents or how many molecules are involved? Only one is involved. That's the reason why this is a unimolecular. This is a unimolecular. And that's the reason why we call it as E1. And what is the type of molecule that this particular rate determining step is including? This is a carbanion, that is the conjugate base. So that's why E1CB. It has one molecule in the rate determining step, slow step. Added to that, whatever the substrate is converted into alkene is the conjugate base. So that way the suffix is E1CB. This is E1CB mechanism, and not all alkyl halides can undergo. There are some criteria to be considered in order to write any mechanism under E1CB. So the first and foremost criteria will be the limitation. What are the type of substrates that can be undergoing E1CB mechanism? So I'll write all the 3 points, you will understand. So E1CB reaction or E1CB mechanism is limited to substrates, is limited to substrates which can stabilize which can stabilize the carbanion, which can stabilize the carbanion as the reaction intermediate, as the reaction intermediate. And this can be done by the presence of certain groups at both alpha and beta position, specifically beta, that is beta carbon. So beta carbon should contain beta carbon should contain strong minus I groups. Minus I groups in the sense electron withdrawing groups, so that the negative charge of the carbanions can be distributed evenly or distributed throughout the molecule. So for example, you can have nitro groups, cyano groups, or sulfur SO2 groups, something like that, sulfonyl groups. Yeah, minus I group, don't write SO2, it is electron deficient. So NO2, CN minus, etc. As long as you have electron withdrawing groups to stabilize the anionic part. Here you can see this is carbon with a negative charge, right? Chlorine is also more electronegative. It can undergo the shift in electron cloud, so delta minus, delta positive, delta minus, and 2 delta positive. So the minus I groups on the beta carbon will stabilize the carbanion formed as the reaction intermediate. So that is the first and important criteria for a molecule to be considered under E1 mechanism, to be considered under E1CB mechanism. Now, second one, this is regarding the leaving capability. The reactant should contain a poor leaving group, otherwise carbanion cannot be formed. So if you remember again, E2 mechanism of alkyl fluorides, just because fluoride was not easily removed, there was a negative charge on the beta carbon. Here, the way the negative charge appearing is different, but end of the day, fluoride will not leave that easily, right? It is a poor leaving group, and that's the reason why we are able to get a proper carbanion. So the type of leaving group will also determine whether E1CB mechanism is possible or not. Could you please explain the first point? Okay. So when it comes to the first point, we are talking about specific substrates which can show E1CB mechanism. So those are the ones with strong minus I groups on the beta carbon. Why? Because after the losing of H plus in the conjugate base, we are having a negative charge rate, that is a carbanion. Carbanion stability is directly proportional to the minus I groups present. So if minus I groups are there, one second. So if minus I groups are there, then only the compound, the carbanion, the so formed carbanion will be more stable. That's the reason why beta position, especially beta group, beta carbon should have minus I group as a substituent. Why? Because this beta carbon is the one with a negative charge, right? So minus I group should be there to stabilize the carbanion form. Now the second thing is the formation of carbanion will further be like, how do you say, will further be easily formed if there is poor leaving group on the alpha carbon. Why? Because if you remember in the alkyl fluoride dehydrohallucination, just because fluorine was not in a position to leave, we ended up having a carbanion. Here also, whatever the carbanion is formed, in order for it to be stable, the alpha position should have poor leaving group. Then only the carbanion will stay as carbanion. If it is a better leaving group, this also can be removed and it will directly form an alkene without this intermediate as carbanion. So but the poor leaving group is also important criteria for the substrate to show E1CB mechanism. All right. And the last criteria is acidity of the beta hydrogen. It should be easily removed. So beta hydrogen should be highly highly acidic so that it can be easily removed. It can be easily removed to give a carbanion. To give a carbanion. So simply carbanion formation should be easy. Ma'am, doesn't carbanion formation takes place in E2 mechanism? No, only in case of actually E2 mechanism reaction intermediate is a neutral species. Only for alkyl halide we will get a carbanion. That was the alkyl fluoride was an exception. Other than that, if you remember the starting of the E2 reaction, the reaction intermediate is a transition state species, a neutral one. It's not a carbanion. Carbanion formation is limited to E2 mechanism of alkyl fluorides and E1CB mechanism. Okay. Only carbocation, a positively charged reaction intermediate, will be there in E1, neutral species for E2, and carbanion as reaction intermediate for E1CB. Okay. All right. So what are the specifics? The substrate, the reactant should have minus I group attached at the beta position, and whatever the hydrogen we are removing from the beta position should be more acidic, in the sense it should be easily removed, then only a carbanion will be formed. And further to stabilize this carbanion, minus I groups should be considered. Along with that, whatever the alpha position we have, that should be a poor leaving group, like fluorides mostly should be there at the alpha position. So these three are the criteria for a molecule, for a substrate to undergo E1CB mechanism or E1CB elimination. Since we have discussed stereospecific and stereoselective definition, let's try to say if E1CB is stereospecific or not. So if we say stereospecific, so is there any specificity towards the stereospecific beta hydrogen removal? Yes, there is specific, because we are removing beta hydrogen in a specific manner, in such a way that we end up having a carbanion. So we are carefully removing, selective removal of beta hydrogen so that we end up with a carbanion. So E1CB is a stereospecific reaction. And when it comes to stereoselectivity, it is not stereoselective. It is not stereoselective. All possible isomers will be formed. All possible isomers. No major product, nothing like that. All possible isomers will be formed without any selectivity. Like as long as beta hydrogen is there and we are in a position to remove it and the reaction proceeds to carbanion formation, all possible isomers, like whatever is possible by the removal of that particular beta hydrogen, all of them will be formed equally. So this is not stereo selective, instead it is stereo specific. There is no preference for the reaction. There is no preference for the type of isomers formed at the end. Okay, what's the time? Okay, we have 2 minutes. All right. You want me to show the reaction step? Okay, these two are the steps, ma. Example with the steps. So this is about E1CB, E2 and E1, all sorts of elimination reaction. So if you see the syllabus for Saturday, when it came to preparation of alkenes, first one was dehydrohallucination of alkyl halides. So all mechanisms we have seen, right? So in tomorrow's class, we will see this dehydrohallucination part all together. We will write those examples, and then we will see dehydration of alcohols part. So that will be the syllabus for you from this alkenes chapter. Last part, could you show? Yes, I'll show. Other person was asking mechanism. Okay, so this is the last part. So when it comes to E1CD, this is stereo specific but not stereo selective, because all sorts of isomers will be formed. Selective removal of beta hydrogen, so that we end up having a carbanion. Okay, all right. Wait, I'll minimize so everyone can see. Okay, so yeah, coming to the PTM and all, many of you were having doubts, right? So they will give a particular slots, ma. In those slots, you have to come, and they will give you the schedule. Actually, one day before it, like when I inquired AO, he told that one day before they'll give you the slots, like what's the slot allotted to you. So accordingly, you can plan for coming to PTM. For us, it's on Friday and on Monday. So make sure you attend so that at least we can get to see, we can interact personally. All right, you have class, right? You can, others can leave the meeting. Those who are writing, they can stay back. Others can leave the meeting, and you can go for your next physics study. Is GOC also combining along with this? Yes, electronic effects are also included along with this. It is gonna be hectic. Even I'm worried. How can I revise all these things in one class, because more time will take. But anyway, we will plan something. Yes, GOC will also be coming. The electronic effects, inductive, conjugative, resonance, mesomeric, electromeric. We have to revise again. Electronic effects, nomenclature not required, electronic effects only, starting from inductive effect to the last hyperconjugative effect. Okay, others can leave for your class. Those who are writing can stay back and finish. And tomorrow morning, I'll let you know tonight what time you have to log in. Tends to complete the portion for Saturday's test. Acha, even I'm tense, not only you, but I'll tell you one tip actually. Concentrate more on alkenes, and normal definitions of inductive effect. Like standard definitions will be there, right? Go through them. After you complete these perfectly, go for proper electronic effects examples, like comparing the acidic strength, comparing the stabilities and all. Since alkenes and alkanes are new chapters, more concentration will be given on them. So first do that. Acidic characters of phenols and all not there. They are there. That's what I'm telling. I was just telling you the order. Like you told that you are going tensed, right? So first finish alkanes chapter, ma, preparation, and then you go for alkanes, whatever we are doing right now. After that, you have ketoenol. At least we can expect two questions from ketoenol tautomerism. At least one. Okay, fine. So in the next part, you go for electronic effects. Electronic effects. First, you start with the basic definitions. The important criterias are there, right? And then you go for acidic strength, basic strength, and stability orders, because these are the most confusing parts. I'm just telling you an order for your comfort. If you want to follow this, you follow. Otherwise, you can leave it, do your own way. But those who are little tensed about how to do the revision and all for Saturday, just follow this order. First finish alkanes, then alkenes, whatever we are doing right now, then revise ketoenol, then go for electronic effects. Don't miss all sorts. Inductive, resonance, both types, plus and minus, electromeric and hyperconjugation. Go through the definitions, the criteria for the molecules or the groups to show this particular electronic effects. First you finish that. After that you go for comparison and all, because by this time you'll get clarity, then this comparison will be easier. Okay, and still any more? Will the PTM be held at Miyapur or Kukatpalli? As of now it's at Miyapur only, ma, because all faculty will be available at Miyapur only. It's Miyapur. It's Miyapur only. Okay, still any more doubts you have? All right then. That will be for today.